So basically what we want here is to define, we are not going to run through all the terms because we are going to be referring to them on the fly as we use them, but we have to define some basic ones. So this chapter is basically there for you to consult whenever you need, and it's also for us to open it whenever we need to clarify a concept. So most of these concepts, or I think all of these concepts, are referred into the rest of the presentations in orange, so that you know that they should be here at least. So the first thing that I would like to define a little bit, or that's how we think about it in ESM-Tools, is the concept of simulation, run, and restarts. So a whole simulation, what is it? Well, it's basically an experiment that runs for a continuous period of time, and it's sharing a common setup, right? So it's basically an experiment, right? And an experiment is made of different runs, runs or legs. So basically a run is a chunk of the simulation that runs completely under one single Slurm job. So that means you get this little chunk of the experiment and you submit it to the HPC, and then the HPC does it inside the wall time that is allocated for you, and then the run is finished and is ready to start the next run. And then what happens at the end of these runs typically is that that the models are going to be writing restarts, and then the next run is going to be reading the restart. So basically the restart is the action of configuring, submitting a new run to Slurm, and that is using like the previous state of the end of the previous run. So this is important because we are going to be talking a lot about run folders, run files, etc., etc. So yeah, but I think is that all clear for you? That's probably pretty natural already for you. And I have to say, we use exchangeably run and leg. So if you hear me say leg, then you know that I'm talking about a run too. Okay, so do I need to go through the definition of lists? No. And dictionaries? So you all know Python, right? Okay, good. Probably the most important part of the dictionaries that I would like to, what I would like to say though, is that in YAML, a list can look like this. So you can build a list with the brackets, the square brackets, or you can make a list just by indenting with this minus here. Okay, and that's basically how you define a list. And a dictionary, as you know, you can have multiple dictionaries nested into each other. In Python, you can recover them with the keys, with the successive keys. And in YAML, that's basically the way you define a dictionary. In Python, you typically need the curly braces, but in YAML, you just have to indent. It's very important that in YAML, you indent with spaces. YAML doesn't like tabs at all.
Many editors have the option that it says map tabs to key. So map tabs to 4 spaces. So even if you hit tab, it will replace it automatically by 4 spaces. So it's quite handy if you configure your editor.
Okay, so we've talked already about the YAML hierarchy. Again, the last thing I would like to reiterate is that we have 2 types of files. One are configuration files, default files that someone has put together for you to start running simulations and building models. And those are the machine, the model, the setup files. There are others. And then you have the run script, which is the actual one. Most of the time you are going to be using to configure to finish the configuration of your simulation. And this is what I was explaining here. There are other configuration files, but these are the ones that we are going to be looking most in detail.
There's a question again.
Do we have a style there? You said 4 spaces. Do we enforce this?
We are going to enforce it.
Yeah, that's good. That's good.
Basically,
Because there are some places where it's still 8.
Yes.
And then
And that's the thing. So YAML allows you, as long as once you are inside a nested dictionary, you have to keep the same indentation. But if you go outside of this key, you can use a different indentation. But it's important that inside the same key, you keep the indentation. But we are gonna standardize this to be, because the configuration files, the default on the past was 8, and 8 is too much. And now we are trying 4, but it's kind of a mess. So we are gonna, it doesn't affect the function, but it really looks horrible. Okay, so the run scripts. So we already look at, we already define what the run scripts are, but, and we also define what a YAML file is. So it wouldn't be surprising for you to see this type of a structure. So what we are having here is a dictionary that is called general, that contains a set of variables. And then we have another dictionary that is called FESOM. And we are going to have one for OpenIFS and for ECAM, et cetera, et cetera. And we refer to these first level dictionaries, general, and then the component dictionaries and the computer dictionary, we refer them as sections. This is not something YAML specific. This is something that we are going to be talking about in the section general of your run script. We are meaning inside this dictionary. So that's basically. And something important to mention here is that not all the configuration files have sections. That's the case for the setups. Because we have multiple components there. But it's not the case for standalone models, because standalone models only have one single. They are defining, for example, only OpenIFS configuration or only FESOM configuration. So the sections are present in the setups files and also in the run script, where you actually have to handle more than one component. Feature variables, we already talked a little bit about it. So basically they are variables that mean, in YAML, that mean something to ESM-Tools. There are a lot of variables in the configuration files that mean nothing to ESM-Tools until they don't get referred into one of these feature variables. So the feature variables are actually the ones that activate the actions on ESM-Tools. The rest is just data that is hanging around until you decide to use it in one of these feature variables. This is something, the concept of the finished config file is something that we are going to touch on later, so I will come back to this slide later. And then compilation scripts. So what ESM master does when you run ESM master, it basically takes all the configuration files needed for building that model. It puts together the information, it sort of bakes the information respecting this YAML hierarchy, and then it understands how it needs to compile these models. And once this is done, then it produces a bash script that can be run even by itself to compile that model, and runs this script. So this is a really nice script to look at to actually understand how ESM-Tools is compiling that given model. And you have already this type of scripts. If you have managed to build your model, you can go to your model directory. And if you look inside, you're gonna see for each component, you're gonna be seeing one compilation script. You can open it. That's basically the recipe or what was used to compile your model. Basically what it's doing is loading a bunch of modules, the necessary modules from that are basically, all this information is given from the machine file, from the component, and from the couple setup. And basically it's loading some modules, it's exporting some environment variables that are necessary for running, for compiling your model. And then it's doing the build. So a pretty standard build. Well, depends on the model, but you will have different building commands. And then it copies things around, but that's basically it. Okay. Then we have another file that is the run files. I'm not going to go a lot into detail on this, but definitely I want to say that this is the equivalent of the previous script we've been looking at, the comp script, but for ESM run scripts. So basically ESM-Tools is putting all together all the information about how to run a simulation. And once it has all this information and it has set up the experiment folder, then it prints this information into this file. And this file is going to be submitted to SBatch, so to your job scheduler, to run a run. So not a simulation, but to run a run. And at the end of the run, it's going to submit the following run. And it's going to again produce a new run file, and it's going to again request for submission into Slurm. So the both main ESM-Tools command both make bash scripts that are like the final thing that ESM-Tools activates, move forward, and do the operation that you want to do.
So this is created by ESM run scripts, right? So we don't have this .run file yet.
Exactly.
You only need to say ESM run scripts, and then your simulation can even run for a month, because everything is handled in background automatically. One job is submitted, it runs, automatically submits another run until the whole simulation finishes.
If it doesn't
Wasn't a question, but yeah, we don't have it yet.
Okay. Check mode. We are going to be talking about check mode in both cases for ESM master and ESM run scripts. It basically puts together all the information, but it doesn't submit the compilation file. It doesn't run the compilation script, and it doesn't submit the run file to SBatch. So it's basically for the purpose of testing. At the moment, unfortunately, ESM master is not producing the compilation files with check mode, but we will change that soon. But it's already displaying a lot of information that is needed if you are debugging something. So check mode is something nice if you don't want to invest resources for example, we don't use it so much in ESM master, but for ESM run script it's very good because it basically sets up all the experiment folder, but it doesn't submit. So it just stops right before submission, so that you can go manually into the experiment folder, check that everything is right, and you don't waste your computing resources.
And you don't have to wait, right? If you don't use check mode, some of the process will only happen once the thing actually starts. And if you're unlucky, you need to wait a day, and then you see that it breaks. So,
especially on holiday.
yeah.
Okay, and one last thing of this terminology chapter. So here we are going to be using a lot FESM2. We are going to be using ESM 2.1 and ESM 3, but many exercises are basically using these two models, but editing things in FESM2 because it's what they have in common. So it's very easy to put exercises in common if you are editing the FESM2 parts. So I guess I don't need to go into details about what are the differences. Maybe I'll go a little bit. So basically ESM2 is ECAM 6, FESM 2.1 coupled with OASIS. So ECAM 6, is the atmospheric part, and FESM 2 is the ocean. It uses dynamic vegetation, and it has one version of ESM2 has support for RECON, and work in progress is currently, RECON, I forgot to mention, is biogeochemistry model. And a work in progress version uses PISM, which is an ice sheet modeling. And then we have ESM-3, which is also a coupled model of an atmosphere model, which is OpenIFS, and an ocean model, FESM. And then we have also RNF map runoff mapper for runoff, and then we are coupling all of that with OASIS 3 MCT, and we use XIOS for input output of OpenIFS.